Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the second moment method. Again! So let's review the second moment method. Again, this involves the variance of a random variable x, which was defined to be the expectation of x minus the expectation squared. So that average squared distance from the expectation. The key to the second moment method was Chebyshev's inequality, that for all lambda greater than 0, the probability that x minus e of x, absolute value, that's the distance there, is at least lambda, the square root of the variance of x, is at most 1 over lambda squared. So again, the square root of the variance is the standard deviation, and this says that if you're at least lambda standard deviations away, the probability is at most 1 over lambda squared. We were able to apply that at the end of the last class to prove the theorem that the probability that x equals 0 is therefore at most the variance of x divided by the expectation squared. And this has the nice corollary that if the variance is therefore little o of the expectation squared, then x is approximately e of x almost always. So not only is the probability that x equals 0 go to 0, and therefore x is greater than 0 almost always, but actually we were able to further show that x is approximately e of x, the expectation, almost always. So this is the key to the second moment method. Today we'll be doing some additional examples, and in particular, we're going to focus on the case where we suppose that x is the sum of variables xi, where xi is an indicator random variable for the event ai. Now in this case, we will, for indices i and j, write I sim j or tilde j if I is not equal to j and ai and aj are not independent. So somehow they're dependent events. And then we will define the delta, so this is just a notation for this specific second moment method, to be the sum over these pairs ij, where I tilde j, so where I depends on j, of the probability of ai intersect aj, that both of them happen. So what good is that? Well, when I is dependent on j, then the covariance of xi xj, which factors into the variance since we're doing a sum of variables, is again by definition e of xi xj, so the expectation of the product minus the product of the expectations, which of course is at most the expectation of xi xj. Since they're indicator random variables, they're 0, 1, their expectations are always non-negative, so that right-hand term is always going to be negative. And then we know that this is at most e of xi xj, and so that will equal the probability that ai intersect aj, as they're just indicator random variables. So when I is not equal to j and I is not dependent on j, so when they're independent, of course, the covariance is 0. So what good is all of that? Well, we can then conclude that the variance of x is at most e of x plus the sum of the covariances. So we showed this last time, that it'd be the sum of the variances, which, since they're indicator random variables, will be upper bounded by their probabilities and thus the expectation. But then that the sum of those covariances, we can replace upper bound with this tilde, this delta. So what does that mean? So if we can just bound delta, if we can just bound these probabilities, these covariances coming from the dependent pairs, then we can make progress. In particular, we have the following corollary, that if the expectation goes to infinity and delta is little o of the expectation squared, then x is greater than 0 almost always, and furthermore, x tildes e of x almost always. So x is around its expectation almost always. So this is just a nice compact way to do calculations. So instead of looking at showing the variance to be little o of expectation squared, here this theorem, this corollary, already does the work and says we can ignore all of the independent pairs and just focus on calculating these dependent pairs, and in particular, if they're indicator random variables, you can upper bound their covariances with the probabilities of the intersections. So that's one formula we'll use, but we'll actually use an even better version of this that applies for so-called symmetric indicator random variables. So we'll say that x1 to xn are symmetric if for every I not equal to j, there is a mapping of the underlying probability space that permutes the m events while sending ai to aj. So this is inherently what we think of as symmetric when they're, quote, all look the same, meaning that we can map the probability space to send the events to each other, the AIs, which for the XIs are indicator random variables, and in particular we can map not only permuting, but we can get any AI to any AJ. So that's what we'll say is symmetric. And now in this case we can develop that formula a bit more, because then delta, which is the sum of these I tilde j, the probability AI intersect AJ, can be rewritten as the sum over I of the probability of AI, then summing over j tilde I of the probability of AJ conditioned on AI. So as you might know, probability of AI intersect AJ is probability AI, probability AJ conditioned on AI. But if you stare at that formula, what you'll notice is that that inner term, that inner sum, is independent of I, and that comes because of the symmetry, right? So it doesn't matter which AI, that sum will be the same no matter the I, since they're always symmetric. And thus, we can actually define a so-called delta star to be this sum. Where I is any fixed index, it won't matter since it's symmetric. So then, given that, we conclude that delta is actually the sum of I, the probability AI delta star, since delta star is then viewed as a constant, not depending on I, we can take it out front, and the sum of those probabilities is, by definition, the expectation of x. So we conclude that delta is delta star times the expectation of x. And hence we get another corollary that if expectation of x goes to infinity and delta star is little o of the expectation of x, then of course delta is little o of the expectation squared, and hence x is greater than 0 almost always, and furthermore x is essentially e of x almost always. All right, so that is what we're going to be using today. In particular, the examples today will be symmetric, so we will be using this corollary as our implementation of the second moment method. All right, so on to the examples. So the first example we're going to look at today comes from random graphs and so-called threshold functions. So we've hinted at this before, but let's define this a bit more formally. The Erdos-Renyi random graph GNP is the random graph on n labeled vertices where each edge is present independently with probability p. So the famous random graph model of GNP, where you put in the edges independently with probability p. And then an important part of the study of random graphs is so-called threshold functions. So we say a function Rn is a threshold function for a graph property P. And again, a graph property is just a property that's closed under isomorphism. So what you would normally think of. So most any graph property, so where the labels don't matter, if when P of n, this probability P, viewed as a function of n, is much, much smaller than R of n, GNP does not satisfy P almost always. So it does, again, parse that word though, it does not GNP does not satisfy P, and that thing happens almost always. So we're saying the complement of P happens almost always, and for P of n much greater than R of n, GNP satisfies P almost always. So what's really going on here is there's this threshold R of n. And if your probability of edges is below that threshold, then almost always GNP does not satisfy P. And once you cross the threshold, once you're greater than Rn, it satisfies P almost always. So this is quite nice. It's not clear that threshold functions exist for all properties, but I'll just tell you it is known that threshold functions exist for the property of containing a given graph H. So it starts out unlikely and then becomes likely, and indeed there is this very nice threshold. And so the question is, what is the threshold function for containing a given graph H? And here I'm saying a threshold function because, of course, up to theta, you could choose different functions, but if you don't care about constants, really there'd just be essentially one. So what is this threshold function for containing a given graph H? That's what we'll study, and we'll use the probabilistic method, the first moment method, to establish some bounds, but we're going to need the second moment method to come in and finish off the proofs. So let's start with a basic example containing k4. So this is maybe the easiest. A threshold function I claim for containing k4 is n to the negative 2/3. This is the probability, this threshold, where when you go above it, you will start containing k4s, and below you almost always do not. All right, so how does this work? Well, let's start in on the proof. So what are we going to do? Pretty standard things. For every s, a subset of the vertices of size 4, we'll let as be the event where s is a clique, and xs be its indicator random variable. And then we'll let x be the sum of these indicator random variables. So x will be the number of 4 cliques in our GNP. And then we're going to note that the expectation of x is therefore the probability of its underlying event as, which is p to the 6th. There are 6 edges in k4. You need each of them, and they're each independent, so you get p to the 6th. And hence, by the linearity of expectation, the expected number of 4 cliques is this sum, which is n choose 4 times p to the 6th, which is approximately n to the 4th, p to the 6th over 24. All right, so we've done the first moment bit. We've established the expected number of 4 cliques in our graph depending on p. And now the question is, we have to argue that when p is much smaller than n to the minus 2/3, that somehow this is unlikely and we don't have any. And then when it's larger, we need to actually argue that there is some, that x is greater than 0, that there is a 4 clique. So case 1 would be then, and you shouldn't view this as cases, I'm just doing it for your benefit, but in the proof you'd write these as separate things. Again, we have to prove 2 statements. So for our first statement, we consider when p of n is much, much smaller than n to the minus 2/3. Well then, e of x is little o of 1, and hence x equals 0 almost always. So if you look at that n to the 4th p to the 6th, you'll note that that number is much, much smaller than 1, given the assumption. And so then via the first moment method, the Markov's inequality, we just know that x actually has to be 0 almost always, since again, x is integral there. All right, so we've done that. And now what else can we conclude? Well, in the second case, we need to assume that p of n is at least n to the minus 2/3 and try to show that x is greater than 0 almost always. So this is where the second moment method comes in. So we'll note, though, that in this assumption, we do have the nice property then that the expectation of x goes off to infinity, which is important for that corollary involving the delta star. So we expect as we grow many of these 4 cliques, but we have to actually show that with high probability there's at least one of them. So this is where the second moment method comes in. So since the xs are symmetric, since these indicator random variables for the various 4 cliques are clearly symmetric, we'll consider this delta star to do the work for calculating the variance and covariances. All right, so let's proceed with that. So we'll just note, though, if you have 2 4 cliques, s and t, so 2 4 sets s and t, that these are dependent if when s is not equal to t, because again, we don't have, when s is equal to t, we just don't write tilde for that. So when s is not equal to t, and they have overlapping edges, right? The event for s only depends on its edges. So we need that they have an edge in common to actually have dependence. And that means that they actually have to share at least 2 vertices, but since they're not equal, they can have at most 3 of their 4 in common. So we know that s intersect t is in 2 or 3. So this is the key idea. We look at our events and we say, okay, which of you are actually dependent events? And now we focus on them to calculate these conditional probabilities. So let's fix s, and then let's go through the cases. If s intersect t is 2, then they have 1 edge in common. And that means that they have 5 edges not in common. So e of t minus e of s is, there's 5 other edges in t that aren't in s. So if we're assuming that s happens, that s is a clique, that first edge is in, but the other 5 are not, and hence the probability of at conditioned on as is equal to p to the 5, since, again, those are independent. Similarly, when s intersect t is equal to 3, then there are 3 extra edges in t that aren't in s, and we need each of those since the conditional probability is p cubed. So now, given this, we can proceed with the calculation of delta star, which you'll remember is this sum over t tilde s of the conditional probabilities at given as, which then you could split up by the s intersect t equal 2 and s intersect t equal 3 terms. and now you have to argue about them. We've calculated the conditional probabilities in each of those terms, but how many are there? Well, there are O of n squared sets t, where s intersect t is 2, because you can choose, once you've fixed s, there's 2 other choices for the vertices of t, so that's roughly n squared. And similarly, if s intersects t is 3, there's O of n sets t with that number. And we thus conclude that delta star is equal to O of n squared p to the 5th plus O of n p cubed. Now what good is that? We want to again compare delta star to the expectation. And the expectation was n to the 4th p to the 6th, so we'll factor that out, and we'll get O of n to the 4th p to the 6th times 1 over n squared p plus 1 over n cubed p cubed. Now if you look at that right factor, we know that since p is at least n minus 2 to the 2/3 is at least 1 over n, we have that 1 over np is much, much smaller than 1. And thus, we can conclude that delta star is little o of n to the 4th p to the 6th, and hence is little o of the expectation of x. And thus, by our corollary, our theorem about delta star, we can conclude that x is greater than 0 almost always. That is, that there is a clique. And again, this was a nice proof wherein we did kind of 2 cases. So when p was small, we could just use the first moment method and conclude that indeed x equals 0 almost always, but to conclude that when the expectation was going off to infinity, that x is greater than 0 almost always, this is where we needed the second moment method to calculate the delta star to get about the variances and covariances. So on to our next example. So our next example generalizes the previous one to all graphs. The key parameter to study is the so-called density of a graph H, which will be noted rho of H, which is the number of edges over the number of vertices. We will say that H is balanced if this density is at most the density of the whole graph for all subgraphs H prime of H. And we'll say that it's strictly balanced if the density is actually strictly smaller for all proper subgraphs of H. So this will be the key to understanding threshold functions, and will indeed prove a theorem that says if H is balanced, then n to the minus vertices over edges is a threshold function for containing H, for this property of containing H as a subgraph. And that should clearly be a generalization, because you can actually see that K4 is balanced, and its number of vertices is 4 and edges is 6, so you'd get 4/6 there, which would be 2/3, which is indeed the theorem from before. So essentially the proof of this will be just mirroring the proof for K4 with a couple subtleties that we'll have to address as we'll be dealing with general graphs H. But for convenience, we're going to let V denote the number of vertices of H and little e denote the number of edges of H. So on to this proof of this theorem of the threshold function for balanced graphs. So it's basically the same. So let's just run through it doing the differences. So now we'll look at all subsets of size V from GNP, and we'll let AS be the event. Not that it's a clique, but just where the event where G induced on S contains H as a subgraph. So these will be the AS's. We'll let XS be its indicator random variable, and we'll let X be the sum of these XS's. So this is somehow tracking roughly the number of copies of H. This is not quite true, as there could be different copies in S. It's tracking the subsets that have copies of H. But that will be good enough for our purposes. And now here's where it gets a little tricky, since we're not tracking individual copies, but just sets. There are most V factorial arrangements for H in a given set S. So what you can conclude is that the probability of AS is at least P to the E, since for one copy, but it's at most V factorial P to the E, as there might be many copies. So we can't get an exact value on this probability of AS, and in general that can be a bit tricky given the different copies can overlap in strange ways, but generally we can conclude, since you think of V factorial as just some constant depending on H, that the probability of AS is roughly P to the E, and so by linearity of expectation, the expected number of copies is this sum of the expectations of XS, which is n choose V probability AS, which is therefore on the order of n to the V times P to the E, ignoring the constants there. So we have almost the same thing we had before with K4. We've calculated the expectation, and we split into two cases. When p is small, so much, much smaller than the threshold of n minus v over e, you can conclude that expectation from the previous slide is much, much smaller than 1, and hence by first moment Markov inequality methods, we know that x equals 0 almost always. All right, so we've done that part. And now we move on to the other case, the harder case where we need the second moment method, that p of n is much, much greater than the threshold. And this is, again, is similar. One, we can already conclude that e of x goes to infinity then, which we'll need to apply this delta star corollary. Again, we can note the x's are symmetric, as the various sets are clearly symmetric, so we can consider delta star. Now, what good will that do us? Well, again, the different sets, S and T, only depend on each other if some of their edges overlap, which only happens when S intersect T is in 2 up to V minus 1. And now we're going to fix S, of course, to calculate the conditional probabilities for these T. We'll fix a T, which has intersection I. We'll note this is where a bit of the subtlety, there are O of 1 copies H and T. So we, again, number of copies of H, there isn't just one copy, there are a number, but again, that's up to some constant, some V factorial. And now for each copy, and here's the key part, for each copy, since H is balanced, we know that the number of edges of that copy that live inside of S isn't denser than the original. So it's at most I E over V of the edges in S. Since there'll be I vertices there, the density can't be larger. So you can have more than I E over V edges inside of S. And so this means that the number of edges from T outside of S is at least E, the number of edges, minus the number of edges inside, which is I E over V. And so the conditional probability here, since there's at least that many edges outside, we'll know that it's at least on the order of P e to the 1 minus I over V. So it has to be quite small, that there's at least this many chances that we'll need for a probability P to have those edges. So that's the key. There's no small subgraph, there's no overly dense subgraph inside, so there's always many edges outside, and so these conditional probabilities are quite small. And that's what's going to save us here. So now we've talked about that subtlety, this difference a bit from the K4 proof. Now we can continue on and talk about delta star, which again is the sum of these conditional probabilities, which we can now write as the sum, a double sum, first a sum over I from 2 to V minus 1, and then the sum over these T. And we'll note that there's again n to the V minus I, such sets T, because basically for every additional vertex, the V minus I other ones you need to pick from T, there's roughly n choices outside. And so that's O of n to the 1 minus V times 1 minus I over V. And now we can just plug this in. So we know that delta star is equal to this sum. And you can actually then note that they both have a nice 1 minus I over E factor. So it's the sum of O of n to the V times P to the E of 1 minus I over V. So why should that look familiar? Well, n to the V, P to the E was roughly our expectation. And we're dividing through by kind of an additional root of that for each of these terms. And since n to the V, P to the E goes to infinity, we can therefore conclude that this delta star will indeed be little o of n to the V, P to the E, which will be little o of the expectation of x. And hence x will be greater than 0 almost always by our delta star corollary theorem. All right, so that's basically the same proof. We just had to be a bit careful in the second case. So first we had to be a bit careful about the probabilities because there could be many copies inside S. And then we had to be a bit careful of how they went about overlapping and used the balance property. So you might not have realized that when we did the K4 proof, we were actually using this balance property to really conclude that delta star sum was small. But here it makes it more explicit how we ended up using that. All right, so that concludes our proof of the balance. That's mostly what I wanted to say about these threshold functions for subgraphs. I will just point out that Erdős and Rényi in 1960 in their paper where they introduced the random graph model, they actually showed not only this theorem, they went a bit further and they said if H is a graph and H prime is a subgraph of H of maximum density, then n to the minus v of h prime over e of h prime is a threshold function for containing h. So what is that saying? It's saying that, so when you're balanced, we know that the threshold function is this n to the minus v over e. And for unbalanced graphs, you look to the one of maximum density. So that's somehow the one that's you really need to get, the thing to look at. And so if you take the one of maximum density, that will give you the threshold function for containing h. Because you'll need to pick up those ones of maximum density somehow first in order to get copies. So you could pretty much derive that from what we've done here. We will skip that and just note that they did that. So that's our examples about containing the threshold functions containing subgraphs. In the rest of the lecture, we're going to look at the clique number of random graphs. So let's go back to GNP and look at the case when Gn 1/2, that p is equal to 1/2, that we used for Ramsey graph. And we're going to talk about what is the clique number of Gn 1/2. So this is clearly related to those those Ramsey constructions. And here, it's a bit of an ambiguous question. What is the clique number? It's a random graph. The clique number depends on the outcome. But what we're asking for is more, can we say anything about what the clique number is almost always? Or somehow, what is it asymptotically almost always? Roughly, what is that number most likely to be? Well, we'll just point out that if you remember, the expected number of k cliques in your Gn 1/2 is equal to n choose k times 2 to the minus k choose 2. So by linearity of expectation, there's n choose k choose possible k sets, and they each have probability 2 to the minus k choose 2. So if you stare at that, you would realize that f of k drops under 1 at roughly when k is 2 log base 2 of n. What good is that? So that means that when k is larger, then this f of k becomes too small. We don't expect too many k cliques to be much larger than this. And so then we can use the first moment type method to conclude that indeed it's unlikely that x will be 0. That it's unlikely that Gn 1/2 would have a k clique that's a bit larger than that. But how can we actually show that Gn 1/2 actually does have a k clique of roughly that order? That is where the second moment method will be used again. So we'll prove a theorem that let k equal k of n satisfy k roughly 2 log 2n, but in such a way that f of k goes off to infinity. So the expected number of k cliques goes to infinity. Then we'll prove that indeed you have a k clique almost always, that the clique number is k almost always, at least k. So let's go ahead and do this. Again, it's very similar to what we've done before, but now the probability is just 1/2, and we're looking at this fixed k around this number. So we look at the various k sets. We say AS be the event where S is a clique, XS be its indicator random variable. We'll let X be the sum of these XS. That's going to be the number of k cliques in Gn 1/2. Then E of X will be equal to F of k, which will go off to infinity by assumption. And so note XS are symmetric, and so we'll consider the delta stars. So what can we do there? Well, again, S and T, the various sets, only are dependent when their intersection is between 2 and k minus 1. They can't be equal, but they have to have at least one edge in common. So we'll fix an S, and we'll fix a T where S intersect T is I, and we'll note then that the probability of A of T given A of S is 2 to the I choose 2 minus k choose 2. So it's 1/2 to the number of edges that are different, that are in T but not in S. And that number is precisely k choose 2 minus I choose 2. So you get this formula. So here we're plugging in, again, we know that P is actually equal to 1/2. So similar to what we've done before, but now we get a very specific number. And now we can continue on with calculating delta star. We'll note that there are k choose I times n minus k choose k minus I sets T that intersect S in I vertices. Why? Because for the k vertices of S, you can choose I of them to be the intersection with T, and then for the remaining n minus k vertices, you have to choose k minus I of them to be the rest of T. Thus, we can conclude that delta star is the sum from I equal 2 to k minus 1 of this number, this k choose I, n minus k choose k minus I, times that conditional probability, which is 2 to the I choose 2 minus k choose 2. Now that might look a bit daunting. Again, we want to show this is little o of the expectation. So how to do that? Well, let's divide by the expectation. And I claim then that when you divide through, you get that this is equal to the sum of I equals 2 to k minus 1 of g of I, where g of I will define to be k choose I, n minus k choose k minus I, divided by n choose k, 2 to the I choose 2. Because we'll be dividing by n choose k, 2 to the k choose 2. 2 to the negative j choose 2. So those would cancel out, and you'll get this term. And this might be a little bit awful to deal with. We could try to use asymptotic methods to give an approximation of this. It's a little bit hard because we want to consider this when I is also somewhat small, 2 and 3 and so on, and so maybe asymptotics won't be so useful there. We could try upper bound methods, but I think it's actually easiest if we just show that g of I is increasing for small I. So if you look at that formula and you take g of I plus 1 and divide it by g of I, you'll notice that most of the factorials say the same, and what you get is the following. You get that I over I plus 1, k minus I over k minus I plus 1 squared, and n plus I minus 2k over n plus I plus 1 minus 2k, and then the 2 to the I choose 2 difference becomes 2 to the I. So it's I plus 1 choose 2 minus I choose 2 there. So we get this formula. Now if you stare at that, what you'll notice is 2 to the I, when I is, at least 2, is at least 4. So it's pretty good. It's at least a 2 squared. What about the other terms? Well, I over I plus 1, I is at least 2. That's going to be at least 2/3. The middle term is actually at least 1, so it's at least 1 squared. And then that right side term, if k, is at most n over 2, and again, k is something like log n, will also be large. So it'll be something like 2/3. It'd be very close to 1, actually. Altogether, you conclude that this ratio is at least 1. So this product of these terms is at least 1, and thus the ratio of the gi is at least 1. And thus we know that gi is actually increasing for our values of I. So all we need to do then is look at the final I when I is k minus 1. So g of k minus 1, you can go back at the formula and look. You get k times n minus k times 2 to the k minus 1 choose 2 divided by n choose k. And we can rewrite that as k n minus k 2 to the negative k minus 1 divided by n choose k 2 to the negative k choose 2. Why would I do that? Well, then the denominator is actually the expectation of x, and the top number can be just written as, at most, 2kn 2 to the minus k. And if I plug in that k was roughly 2 log 2n, you'll get roughly the following, that the top becomes 4n log n, the 2 to the minus k becomes a divide by n squared, and again, expectation of x is going to infinity, so let's just say it's at least 1. And we conclude then that this g is on the order of, at most, log n over n. So it is quite small. And since there are at most k being approximately 2 log 2n terms, we can conclude that this delta star over ex, when you sum up those, it's on the order of log squared n over n, which of course is little o of 1. And thus, x is greater than 0 almost always. So we've used our delta theorem / corollary to prove this, and we've concluded that indeed we always get a clique of roughly that number as desired. So that was our proof for the clique number for GN1/2. I'll just mention that Bullet-Bosch and Erdos, and separately Matula, both in 1976, used this and did it a bit more to show that there exists a k equal kn, such that the probability that the clique number is k or k plus 1 goes to 1. So what are we saying here? We said k roughly being this 2 log 2n. We didn't work out the specifics, but if you work out how those numbers jump around, you can show that actually most of the time it's going to be one specific number that dominates with the probability, but then actually there could be some numbers where it somehow straddles 2 values. But you can actually show, and that's what they did, that it will asymptotically always be one of 2 values for a given n. So for all n, it will always be one of 2 values. Most n will be 1, but actually for some it could straddle 2, but it will be 2. So that's a very nice theorem that showing that it's actually rather tightly concentrated on this very specific function, this very specific values. Here we just did a bit of that where we showed that somehow approximately it was this value of 2 log 2 choose n. So we won't do that proof, but again, a nice second moment method proof where we did the hard part of showing the clique actually exists by considering the various, the delta star, the various covariances, these conditional probabilities. So that concludes our lesson for today, where we saw various examples for random graphs, for threshold functions, for cliques in GN1/2, and we're able to use the second moment method to actually show that cliques do happen almost always if these probabilities are large enough, and that's something that the first moment method could not do. So until next time, see you then!